I didn't record. I just started recording. Well, this is a perfect time to start recording because we're getting into the example. Is there anybody else that that is experiencing connectivity issues? I just started recording, so when I left and came back, everything went back to normal. Well, I'm recording this. What I'm going to do is I'm going to upload this to YouTube when this is all done. So, so that way that if for some reason anybody's having any issues there, we can go back to YouTube. Oh man! All right, let me stop the sharing. So you all should see me now, and then. All right, does everybody see the notebook? Okay, good. Awesome. All right, so we're going to get right into this. I have here this beam, and like the last time, I've given you a lot of the design values from before. Again, we're going to assume that 50% of the load is sustained for a period of 6 months. And let's just get right into this. So first off, we're going to compute our moments. So our dead load moment is WL squared over 8. And that is 57.6 foot kips. Our ML is WL L squared over 8. So 2.4. Yep, there you go. And this is 172. I probably should have waited on that, but I've got some other values I'm going to wait for you all to help me out with later. I figured this one everybody's comfortable with. Now, dead load moment and live load moment are pretty straightforward. We also need our sustained live load moments. So this one's new, okay? But this is really easy, okay? If you look at the problem, what we're going to do for this beam is we're going to assume that 50% of the load is sustained for a period of 6 months. So our sustained live load moment is just 50% of the live load moment. So 50% of 172.8. So this is, this is 86.4. And I'll also go ahead and put this over here. I'll say note. Our sustained live load, like the actual load, would also be 50% of the live load, which is 1.2. All right. Any questions on that? I got to believe that that part is pretty simple. And I want to wait just to make sure that if we had any issues with connectivity, if there was anything that that caused an issue, I want to make sure that we're good there. Okay. Now, what I'm going to do now is, because this calculation is so repetitive, I'm going to do things in a little bit of a different order than I did last time. Last time, what I did is I took each stage and I computed its moment of inertia, and then its deflection, then moment of inertia, and then deflection. Instead, what I'm going to do right now is I'm going to compute all of the moments of inertia all at the same time. And that's just because, again, because it's so repetitive. Okay, now let me write down the formula over here on the right to make sure that we're comfortable with this. So IE is 1 on the bottom, 1 minus 2 MCR 3 MA squared 1 minus ICR over IG. And then all under ICR. Okay, just to make sure we all have that reference. So in order to compute an IE value, you need 4 quantities. A gross moment of inertia, a cracked moment of inertia, you need a cracking moment, and an applied moment. So the way I'm going to handle this is I'm going to actually draw this in one big table. Okay, so let's look at our stage. Let's look at our cracking moment. Let's look at our applied moment. Let's look at our gross moment of inertia. I'm surprised you didn't do it this way Wednesday. That's the reason why I didn't do it this way Wednesday is because I wanted everybody to see how the dead load deflection changed from stage to stage. But because we got so many to compute this time, now I'm being a little lazier. I do like my tables though. All right. So we've got our stage, our 4 values, and then the IE value. So remember, when you're computing total dead load or total deflection, you need to directly compute 3 deflections. The first is the dead load deflection. So for the dead load deflection, what do we have? We've got our cracking moment is 45. We've got our gross moment of inertia is 16,000. Our cracked moment of inertia is 9,000. But what about MA? MA is the value that changes. And for the dead load, MA is MD. So it's 57.6. So we've got an MCR of 45, an MA of 57.6, an IG of 60,000, and an I cracked of 9,000. So somebody in chat tell me what's IE for this data. Anybody got an answer for this one, for this IE value? Yeah, we're just using this equation up here. My value came out a little different. Maybe check to see if you're squaring your exponents or your parentheses. Yeah. No, I got what Mr. Schwartz got. I got 10,211.9. Yeah, that's what I got. So I would say if you're ever having, yeah, and that's easy to do. I've done that before too. For the check your order of your values, it might be worth it to just compute your denominator by itself and then do ICR divided by that. Okay, well, let's go ahead and do the next one. And we'll see if we can work out the next one. Now, the next one is dead plus the live. And the nice thing about setting it up in this table format is everything except for MA is the exact same. The only thing that changes is the MA. So now we have the dead plus the live. And so instead of using 57.6, we use 57.6 plus 172.8. And so that comes out to be 230.4. So maybe what I'll do up here is I'll say MD plus L is 57.6 plus, which is 230.4. And then MD plus SL, which we're going to do later, is 57.6 plus 86.4, which ends up being 144. All right, so somebody have an IE value for the second stage? $9067.3. That's what I got. And then for the next stage, there you go. This one's 144. Everything else is the same. And then what about for the last one? Yep, that's what I got. Not too bad, right? Should be pretty comfortable with that calculation at this point. So now we're going to look at our staged deflections. Now I want to make a point on this. We're going to do this in a similar fashion. We're going to use a table. I'm going to put a couple notes before we do that here. First off, note every case for what we're about to do is a simply supported beam and a uniformly distributed load. So I'll say that delta at the center line is 5 WL to the fourth over 384 EI. Okay, so that's going to be my first note. My second note, and this is going to be kind of important for your homework, is I'll say, be careful, don't use that formula. Oop. I did. We're going to add 0.01 to the mistake counter. 74. 0.02. I'll be generous. All right. So the second point is be careful. Don't use that formula for other load cases. And I guess it should say also be careful using a table. And the reason why I say that, and you're going to see this here in a second. This second note that I put here, this is going to become clear here in a second. Now, again, because we're dealing with a simply supported beam and all the loads are uniformly distributed, this is going to be pretty doable. So we have our stage. We have the same three stages, D plus L, and D plus SL. Now, look at our formula. Our formula says that 5 WL to the fourth over 384 EI. So we need a W. We need an L, we need an E, and we need an I. And we do that to get a deflection. Now, a lot of these are really easy. So the length, this beam is 24 feet. So it's 24, 24, 24. The moments of inertia, we just get these moments of inertia from what we literally just did. So 10,000 to 11.9, 9067.3, and 9174.2. So that one's easy. The E value, if you remember at the beginning, we were given the E value, it's 4,000. Remember, I had a typo in my slides, but I caught that. Yep. We got to go with another mistake on the mistake counter, 0.01 on that one for sure. KSI, you're exactly right. That one's KSI. Now the distributed loads. The distributed load, you're telling. The distributed loads are in kips per foot. Now, if you remember at the very top of the problem, I had did this over here on the right. So the dead load is 0.8 kips per foot. But see how I have the live load and the SL over here? So maybe I'll put this over here. So W dead is 0.8. W live is 2.4. W sustained live is 1.2. So just writing that so I don't have to keep, going back and forth, back and forth. So this one is going to be 0.8. This one's going to be 3.2. And that one's going to be 2. So now what I can do is for each of these deflections, I can just do 5WL to the 4th over 384 EI. However, don't forget your 1728. Don't forget that because we have to keep our units consistent. So help me out. Somebody tell me the dead load deflection. The first one. All right, that's what I got. And yeah, let's keep it to 3 decimal places. 0.146. How about the second one? Everybody got the second one for me? Yep. And the third one. Somebody else. Yep. Exactly. So remember when you compute deflections, you can compute your staged deflections directly, but if you want to get the deflection, say, due to the live load, you have to take the deflection due to the dead plus the live minus the deflection due to the dead. So that is 0.659 inches minus 0.146 inches. And so that comes out to be, it's like 0.512, I think, with rounding. And then for the sustained live load, it's the same story. We take the dead plus the sustained live load minus the deflection due to the dead, and that is 0.407 minus 0.146, and that's 0.261. Okay. Everybody good so far? Well, the rest is pretty simple. Okay, so we need to look at total deflection. All right, so we have our dead load deflection, which is 0.146, our live load deflection, which is 0.512, and our sustained live load deflection, which is 0.261. Now remember, the formula is our total deflection is our live load deflection plus that times our dead load plus that times our sustained live load. So we need a couple values. Now, first off, our rho prime, I'll go ahead and give you the formula for rho prime. It is the compression steel divided by BD or BWD, but this beam doesn't have any compression steel, so this is going to be 0 square inches divided by whatever this is, but it doesn't matter because that's 0. So rho prime is 0. So the only thing left we need to figure out is this this xi factor, this time-dependent factor. So let me cheat here a bit. So this is the curve that that I provided in the slides. Hold on. Let me move that over here a bit and make it a little bigger. Ooh, that's probably good. Now, if you remember, I said that that this load for this problem, we're going to assume that it's sustained for a period of 6 months. So if you follow this up here for 6 months, and then look at the graph, we're getting a psi value. Sorry, hold on. We're getting a xi value of about 1.2. And that's coming from the curve. You can also review the the table that they provided. Remember, this was the table in the slide, and they said that if you had 6 months, that it was 1.2. If you're ever not in a row in the table, you would go to the curve. So therefore, the calculation's pretty straightforward now that we've got everything. So therefore, our delta total, is, so we have our live load deflection, which is 0.512 plus, and then we have 1 plus 50 times 0, which all that's going to be 1, so it's just going to be 2 times dead load is 0.146 plus 1 plus 50 times 0 over 1.2 times 0.261. Anybody got a full deflection for me? I'll give you all a second on that. $1.117. That's exactly right. Now, that is the answer. Now there's something else I want us to go ahead and try and do before we close it for today. Let me stop this share real quick and go back to the PowerPoint. So if you go to the problem said determine the total live load or the total long-term deflection on the beam. So the long-term deflection end up being 1.117 inches like we just determined. But if you look at the bottom, it says also determine if the ACI requirements are met. Now it says assume that this is a floor beam supporting attachments that are not likely to be damaged by large deflections. So where that comes from is if you go here and you look at the table for deflections, when you're looking at long-term effects, there's two conditions. If you look, it doesn't matter whether you're looking at a roof element or a floor element, but is it supporting elements that are likely to be damaged or elements that are not likely to be damaged? So we're going to say that it's supporting elements that are not likely to be damaged by deflection. So to give you kind of an idea, if you're designing like a hospital, the room that houses the MRI machine, you have some pretty significant serviceability limits there because you don't want the floor deflecting too much because that can mess up the machine. So that might be an element that is likely to be damaged by large deflections. But like an office building, like if the desks move around, that doesn't really affect anything. So we're going to use the not likely to be damaged by large deflections, so L over 240. So if you go back to sharing, let's go to share application. So we'll say the deflection limit is L over 240. This beam was 24 foot long. Don't forget we need to throw a unit conversion in there to get that into feet, or sorry, to get that into inches. Then our deflection limit, so 24 times 12 divided by 240 ends up being 1.2 inches. So therefore, ACI requirements are met. Because the deflection that's actually, the beam is actually 1.117 inches, and its maximum deflection is 1.2, so it's less than the limit, so we're good. If we weren't good, we would have to change the dimensions of the beam. We'd have to, make the beam bigger, up our I values accordingly. Any questions? All right, let me real quickly, will you post the example from today online? Are you talking about the video? The video will be okay, yeah, so it's recording now, and so I will try and get that uploaded to YouTube as fast as possible, but you can always access the recordings through Collaborate as well. I sent an email a little while back on that, but yes, I will. Let me pull up the homework because I want to show you all something. So this is the homework assignment for this weekend, and this is the exact same problem from the last homework. The loads are the same, the dimensions are the same, even the IG and the ICR, all that stuff is the same. And instead of computing immediate deflections, I want you to compute long-term deflections. Now, you can use the solution to this homework to help you with, or you can use the solution to homework 7.2 to help you with this homework because it's the same problem. I am going to post that homework either Saturday or when everybody turns it in. And I looked on Blackboard and it looked like most people had turned it in. I was still waiting on like a couple. But if the sooner everybody gets it to me, the sooner I will post the solutions. So yeah, but at the very least, I am submitting, putting the solution out on Saturday. Everybody good? All right, well, for those of you that are not in steel design, have a great weekend. And for those of you that are, I will see you here in a couple minutes. That's all I got.